this is half of the class. This is not good for me. Sorry. Okay. So today we progressing in this eigenvalue and eigenvectors, and what is new is the eigenspace. We just start this eigenvalue and eigenvectors. Blah 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 blah. Okay, there are some definition, and the subspace was mentioned. Okay, you have an operator, any operator, and the eigenvalue problem is very simple. This operator could be called matrix, transformation, whatever you want. You are looking for a vector for you applying this function, the operator or matrix, and you got the same vector, or almost the same if you not consider the length. So this vector name is eigenvector, and the other name is eigenvalue. This is very, very, very important. Imagine if you have, for example, a transformation matrix. Yeah, you didn't like the transformation matrix. No one liked it. You did a different way in the test, I think, the rotation, but not a problem. It's okay. Actually, could you write my handwriting, because I just uploaded the solutions.
I didn't see it on Teams. I haven't looked at it.
Okay, then yeah, I ask one person. For example, rotation. You have a rotation around the z-axis, then that's a matrix. And in this case, all the vectors not parallel, the z-axis is an eigenvector, and all vector which are not parallel but is along the z-axis are an eigenvector because they don't change. The rotation will not change. If you don't consider just one, if you don't consider the length of the vector. I gave this. Okay, so for example, if we are in 2D, Okay, this is what I'm talking about. You have a rotational matrix. I hope the signs are fine. And if you have a vector which is on the x-axis, then if you do any rotation, then you got the same vector. The algebraic problem is this: you have an operator, you have a function, and you should get the same function. Here, this is an operator, and this is a lambda number. You also can write and of course so that was the eigenvalue problem, and there are many applications. We learn how to calculate it. If you write down this, you write a determinant, you got a polynomial, you have to write polynomial as an equation, and then you will get the eigenvalues, and you also can get the set of eigenvectors. Now, this is a repeat. I will do examples and everything. But when you are very, very confused, we can jump to here. This is the Leverrier-Sorieux algorithm. I copied and pasted from Wikipedia. Why I did it? This Leverrier is very, very important guy. He was an astronomer like me and discovered the Neptune. First, William Herschel, calculated, wait, perhaps I'm wrong. Is it Neptunus or Uranus? He was considered as mathematician, actually, and worked in this Paris observatory in the 19th century. The web is horrible. I'm in the Wi-Fi. Next. Classical, if you without a telescope look to the sky, you can see six. Mercury, it's very rarely visible. I saw only once when I lived in Germany, and we are about exactly looking to the west, the 11th floor. The Venus, which is visible after sunset right now. Mars, it's a nice, very light sunset. Jupiter, it's always bright. Saturn. And also the name of days are corresponding to this name of sun, moon, and also the name of the planets. The William Herschel discovered the big telescope. It had the lenses, not mirrors. The Uranus, and the Uranus orbit was not so good. There were some disturbances observations, and based on them, they predicted where should be the eighth planet. This was the Neptune, and this Leverrier guy discovered it. Why am I talking about this? Because it's interesting, and I'm sleepy, and whatever. Now we also have only 8 planets, because the Pluto is not a planet anymore, it's a minor planet. But I'm charged to explain you this Leverrier-Serre algorithm. The problem is that there is no Leverrier-Serre algorithm, and it is a method. There was no computer in the 19th century, and they could not calculate with computers with this. And Leverrier developed this algorithm. There was another French guy, Soru, I don't know how to pronounce, who refined it. And the name of the algorithm is something else, something Fabre-Leverrier method, and not algorithm. And what is it? This is an easy method to calculate the eigenvalues of a matrix. So you have determinants, you have a lot of things, and you will find it on the themes, because I will not talk about it. Why? Because I don't see the sense of talking about it. Even we have an example. Perhaps tomorrow I will explain you. I don't know what is this. So this is absolutely nonsense. You are learning chemistry. I have a list what to teach you, but it seems to be whatever I had taught you, you don't use it. You are in your second year. Okay, so the eigenvalue problem, I will talk about it. It's important. For example, if you have this impulse momentum, it's like the impulse just for rotation. Then the one stuff is a tensor, and its eigenvalues are the values of this object, and there are a system of vectors, and these are the eigenvectors. If you have an asteroid, and you, for example, approach the surface of the asteroid with the rotational ellipsoid, it has one main and two minor axes, approximately. It's potato. Then more or less they will be the eigenvectors. If you let alone for a long time, really long time, this asteroid, then after a while the rotation will rearranged, and the asteroid will rotate around that axis, that eigenvector, which has the largest eigenvalue. Very nice, but here this is absolutely useless. But I gave you the formulas and everything. However, there are more interesting stuff that I can explain you. First, a jump back, because this is not acceptable. For example, you have this matrix. And you are looking for the eigenvalues and eigenvectors. What you could do, you have to fix this equation. What is this equation? This equation is if the x is a null vector, then that's the trivial method, and we cannot do anything with it. We need the other stuff, this a minus lambda to be 0, and that's a perfect. In this case, this if you start calculating this, you should have told me that I'm wrong. This is not 2, this is 4. And this is also 4. Okay. Oh, wait. So this is 4. Yes. And then, yeah, 4. Yeah, that's okay. But this one is it's weird. Okay, so lambda 1 and 2, the eigenvalues are 1 and 3. Okay? Then That's 3. Okay, so this was repeat. What I had done, I have linear transformation, operator, function, whatever I want, and I'm looking for those vectors which are the same after applying this function for them, if I not consider a constant. These are the eigenvectors and the eigenvalues. This is an example. I have this matrix, and I'm looking for this, and I'm looking for the non-trivial method, the solution. I just write down the characteristic polynomial, so this determinant. So this is the A minus the eigen operator multiplied by lambda, the constant. I'm fixing this, and there are two solutions, two eigenvalue, 1 and 3. Okay, but this is half of the solution because I put back the value to the matrix, and I'm applying this new matrix for this general vector, and what I got is all vector is fine, which the second component is the opposite of the first component. This was the lambda 1. I mean, the value is 1. It's lambda 2, but the value is 3. Then this will be minus 1. And then the set of vectors, the eigenvectors, is all vectors which has the same x and y component. Okay, do you remember this?
Yes, yes.
Okay, this is very, very important. Why this is very, very important? There are a lot of things, and sorry for being late because later I will talk about this. Talk about this impulse momentum tensor, that's fine. But have you ever learned about Schrödinger equation? You? You? Quantum mechanics?
No.
You haven't?
No.
Do you know the shape, and do you know the shape of the electron cloud around a hydrogen core, I mean a proton in a hydrogen atom?
The shape of it?
The shape of it. Really? S, P, D, F?
Yes, but we have.
Yes, but what do they mean?
The different electron clouds.
Yes, and how do they look like?
The possibilities of chances is the highest possibilities of electrons included.
Yes.
And this polynomial equation explains that.
What equation?
This polynomial equation explains that the electron might or might not be there.
Okay. What equation? I didn't understand the name. What equation?
It's Schrödinger.
Cody?
Schrödinger.
Schrödinger.
Yeah, the one that.
Schrödinger.
Yeah.
Schrödinger. SCH is okay. You know it,
I forgot about it a little bit.
but you read about you learned about it, or you read about
I
it.
read about it. It's not in the curriculum. Yeah, I only read it online.
It's okay. It's okay. It's fine. The Schrödinger equation is a quite ugly equation. It's a partial differential equation. If it has one part which time dependent, if you not consider this and this time dependent stuff, you got an eigenvalue problem. It's quite simple. The other is also an eigenvalue problem. You have an operator. The operator describes the potential, the Coulomb potential of the proton. The potential is 1 per r. The force is 1 per r cubic. That's okay. And if you fix it, you got eigenvalues, and you got not only eigenvalues but eigenvectors. Do you know what is Lyman alpha line? Do you know spectra? So the eigenvalues, eigenvalues gives the energy levels of the electron around the proton. It's not exact, but it's something like this. It's something 1 per force, but which is very interesting. The first shape is probability. The vector is a probability function. If you square it, you got the probability of where is the electron around the proton, the hydrogen. And you have it's actually not a point, but doesn't matter. The S means square. Then P, it's more difficult. It's something like this. P, D, I will check on the internet if I could. This is not exact, it's ugly. And the F, which is in special metals, it's something and this is an eigenvalue problem, but I look for the internet for this. I should have written in the slides. This is long. So these are the values. Here. It's more difficult. The P is yes. and the D is just they don't S P D S P D F. Okay, so there is no 8, just 4. So this is one application. Other applications, it's difficult, it's not easy. To calculate this, I did 2 or 3 hours when I was a student. Now I would need 2 weeks because I have to learn these spherical functions and everything, and I need more time. And doesn't matter. This is one thing. If you have an object, a solid object, which we have in experimental physics, we had set of springs and balls and everything, and we could write it down as a matrix, and also an eigenvalue problem was the solution. If you have such a building like this column between this one, so between the windows, it's a solid state, and the solid state's simplest model is a compressionable material. And also, it has a very, very difficult eigenvalue problem. In space physics, there is something that's called minimum variance method that I use, and it's also about eigenvectors. So, instead of this horrible method, algorithm, whatever, I just told you some useful feature of the eigenvectors and eigenvalues. It's better, and I will rewrite the syllabus. I will add this in particular. Actually, the real problem with the syllabus is that it is written eigenvalue problem. Great. Yes. Yeah. University of Page. Yeah. Yes. So it's not in a particular. So in details, we are reach this one. Okay. The first thing is actually was not proved. You calculate such a way in practice tomorrow. I will do more. Such a way you determine the eigenvectors, and the eigenvectors set a subspace. And this could be also a coordinate system. Later, next week, we will learn about different transformation using eigenvalues and eigenvectors when not some matrices, not all matrices, could be transformed to diagonal state. From a matrix transformed to diagonal state, it has some advantage. You can determine the determinant quite easily. You also can determine the eigenvalues quite easily, because it is not a, I haven't told you, but a diagonal matrix eigenvalues, of course, the main spur, the main diagonal values. Also, you can calculate the inverse quite easily. So there are such methods. Blah 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 blah. So there is an A matrix. There is an eigenvalue of A, and then there is a set of eigenvectors corresponding to lambda. I mean each lambda, and this forms a subspace. Okay, what's this? Okay, doesn't matter. So that's a subspace. Next one. This subspace is called eigenspace. Okay. Next one, which is important and nice. Triangular matrices. Okay, here there is a mistake. I talk about upper triangular matrices, where you have 0 elements in this. No, I talk about upper and lower diagonal matrices, and the upper triagonal, there are only 0 below the main diagonal, and it's the opposite for the lower triagonal. But there are other decomposition of matrices, LU, QR, and everything. I will talk about these very soon. So the statement is that the eigenvalues of a triagonal matrices and of course the diagonal matrices are equal to the elements of their mean diagonal. Actually, this is logical. If A is a triangular matrix, then the sum total subtract of diagonal matrices, also triangular matrices. So this A minus lambda, here is either identity matrix, but that's A, is also a triangular matrix. And this diagonal matrix determinant is the product of its diagonal elements. So you can write that equation, and these are the eigenvalues of A. Okay. Okay, here you if you want to calculate the eigenvalues, then this one and this one will be 0. This one is 0, this one 0, everything else is 0. So this is the free eigenvalues, which is interesting. Okay, so this is it. This is just an example. The life is easy with the triangular and the diagonal matrices. Okay. Actually, this is not really a statement. The statement is first, if you have the eigenvalues, then the determinant of the matrix is the product of the eigenvalues, and we have a new term, this trace. This is the sum of the eigenvalues. And just a moment here. This is, yes. For this, at least it's okay that this is the determinant is the multiplication of this. Then just a moment, if you have that seems to be right. Okay, and this is better. For 2 times 2 symmetric matrices, then the eigenvalues are real. The A has 2 identical eigenvalues. And the vectors, the eigenvectors, set a plane. And the eigenvectors are orthogonal to each other. Okay, we had the matrix has an inverse. They are regular matrix. If the eigenvalue there is no 0 eigenvalue. It's easy to prove, to deduct. And then You have a general matrix, which is a square matrix. There are more actual statements here, but I took only two. If A is symmetric, then the eigenvalues are real. If they are skew-symmetric or antisymmetric, then all of the eigenvalues are imaginary. You have learned the complex numbers, didn't you? It's okay. Okay, so, okay, there is a deduction. Okay, and okay, and here is our monster, this Leverrier Soto algorithm or whatever. What is it that I just wrote down and not really know why. And that's it. This method, I cannot tell you where you can use it. Perhaps in a numerical algorithm, but will you learn numerical analysis, numerical algorithms? You cannot, you don't develop, you don't learn Python or anything.
No, I did in high school, but we did MATLAB.
I think we have numerical algorithm.
Because this monster that I just not skip but just copy and paste from the Wikipedia. This is a numerical algorithm. Actually, if you have a lot of, I don't know, processors, I mean not very well paid women or something like this, and calculate this, then you can